Hello, this is our presentation for ELMPs for markets, specifically with convex hull pricing variance as price setting structures within energy markets. My name is Ethan Kerr,
And I'm Daylon Veater.
and currently, as of right now, Maui is in DC. So we will add him in as needed um, when when we are good to go. But yeah, we can start off with the first slide. So we wanted to do a crash course on what exactly comes about with the LMPs, and that is our current energy market structure. And within the United States, electricity markets, they use what's called uniform pricing, and that is when the ISO sets a price, a clearing price for all the generators with bids that are brought into the market. And um, this is what the consumers will ultimately pay. It doesn't matter if some consumers bid super high or super low. It is set at one singular price that, as long as it was part of the dispatch, they will all get the same uniform clearing price from uniform pricing. Um, and th this uniform or this market pr gets the uniform price, and it is specified by location, and that is what brings us to LMPs, which are how the system divides it into several different buses, and at each node on the grid, it has a certain price that comes with it, and it is set at its own LMP specifically. And this LMP is simplified to be the cost to deliver the extra increment of power to a specific location, and it is specifically 1 megawatt. Um, and this, by definition, is the dual of the nodal balance constraint and the system dispatch optimization problem. So this is, from a mathematics standpoint, it's the LMP is a dual variable, and in when the system operator goes to solve the economic dispatch problem, it is a convex linear optimization, and this LMP then becomes a shadow price, and it would tell us how much the system would cost if we had to put 1 more megawatt into that load at a specific node. And this will give us a basic understanding of the competitive market because it will reflect real-time operation and real grid conditions at a certain node for a certain price. Continuing on, for LMPs, this is a key challenge because these are convex problems, and convex systems can be defined through a true locational price, and these are what is forming an LMP. And the the big problem is for the ISO that it has to solve for unit commitment. And this unit commitment is not convex. So the generator is either on or off, which then brings in binary decisions. So startup costs, minimum times, things that can break convexity. Because of these, they do it in two stages, which is the SCUC, which is the non-convexity, and it figures out which parts need to be brought up and met with more help. And these are also um, followed into the SCED, which is the dispatch levels. And these are continuous convex. So these are the things that actually produce LMPs. The complication is that these don't cover the commitment problems. So startup fuels, no load costs, and other monetary values that can bring or spike up the costs that aren't seen on the regular level of plane. Um, and to ensure the generators to make sure that they stay financially afloat and are able to produce and participate, ISO provides uplift or make whole payments, and these will help fill the gaps and uh, help bring the LMP revenues and the generators costs afloat or help them keep afloat. And this can create a problem because the price isn't fully being shown because of all these underlying costs. Going on to the next one, uh, we wanted to see some motivation or possibly other sides that can help create uplift payments, or sorry, not uplift payments, but show that it has a full reflective cost for all the underlying parts. And these uplift payments show that the LMP doesn't cover certain parts of these, which is what I previously talked about with all the startup costs, the no load costs, and the other rising costs. Um, and because these aren't included, they have to make separate payments, and this means that it isn't acting as a isolated price, which could also lead to price discrimination, sorry. And these are when some generators will receive special payments, and this is to cover operating or lost opportunity costs, which we speak on later. And this shows that it is not purely competitive because it is bringing an external factor to keep the cost itself afloat or at a uniform price. And so this creates a system or this bridges us into looking for a system where the prices are better reflective and improves transparency on the payment side of it, things. And the ultimate goal is to provide a more efficient and fair market design that properly incentivizes generator behavior without hidden costs. And going on to extended LMPs, we wanted to show that MISO brought in these idea of an ELMP, and this would incorporate the costs that would require uplift payments, such as the startup and no load costs, and it would put it directly into the marginal price. And to do these would be our traditional dispatch model and the pricing model. And the dispatch model still uses the SCUC, and it identifies the constraints and the reliabilities. And then the other side of it is the pricing model, which instead of using SCUC, it uses a pricing model that will relax the binary commitment numbers that we spoke about earlier. And these minimum output levels are softened, and the unit commitment variables are allowed to take smaller values. And this convexifies the SCUC. And once these are relaxed, it becomes a more convex-based problem, and more, this allows it to be tackled by eliminating underlying costs. And these LMP ideas will reduce the size and frequency of uplift payments while providing a price signal that better represents true costs of a real life, real-time system. And these LMPs bridge to aim the gap between economics of a marginal pricing system and the operational realities of a power grid with or that hold non-convex generator constraints.
What is convex hull pricing? Convex hull pricing is the ideal form of ELMPs. As the name suggests, it convexifies a non-convex problem in order to produce prices that reflect all non-convexities like fixed costs, startup and shutdown costs, minimum up and down, and so on and so forth. So how do we convexify? Given that we have a simple MILP problem, we have this two-dimensional space in this photo where we have our solution set represented as points. Convexifying it involves the tightest possible convex envelope, or in other words, it's like wrapping a rubber band around it. The solution space is relaxed and is a superset of the original non-convex solution set. Take note that this is not the same as just relaxing our binary decision variables to be continuous between 0 and 1. Once we have the convexified solution space, which we now call as the convex hull, we can now conduct an optimization over this new convex hull. Here's what the convex hull pricing formulation looks like. It is very similar to a usual pricing problem, except we now relax our decision variables to be within the convex hull. Doing this immensely changes the behavior of the problem, and the intuition we learned from studying the duals of an economic dispatch will not be applicable anymore. To further understand convex hull pricing, let us analyze its dual formulation. So take note that the analysis and the properties that are observed and explained here and the formulation are all taken from the paper listed in the footnote below, written by people from ISO New England. In that paper, the authors decomposed the dual formulation into three major terms. So what are these terms? If you were to convert them into word form, you will get this one. So the key things to look at here is the last keyword, whether it's a revenue or a cost or a credit. So we know that revenue minus cost equals profit. So if we were to aggregate this further, we have the maximum possible profit as the first term, and then the actual profit as a second term. The difference between these two is what we know as loss opportunity cost. So what's interesting in convex hull pricing is we now consider the maximum possible profit, and that amount is a virtual or non-existing amount. We know that the actual payments, the actual revenue comes from actual dispatch, but here we consider a theoretical what if, and that acts like as a ceiling, and now we are measuring loss opportunity cost. Now for the third term, which is the difference between the actual system revenue and system constraint credits, this is what we call the product revenue shortfall. So what is product revenue shortfall? There are two terms here for PRS. The first term is the cost of operating over the system, or the revenue paid to the system and the system constraints. So that could be generation rent, congestion rent, and so on and so forth. The second term is the credit collected from the system constraints. So it is some sort of income for the ISO or the operator. So there is a property in convex hull pricing wherein the system is somehow always incurring some sort of cost even for non-binding constraints, meaning that the total credits collected by the ISO may not be able to cover the total system revenue. In short, product revenue shortfall tells you about revenue inadequacy. Typically, this is common to FDRs and how the system may not be able to compensate them. But with convex hull pricing, even generation and other system components and resources can contribute to revenue inadequacy. Note that this is a non-negative value, especially for this generic formulation. So other properties observed in the paper are the following. Identifying the convex hull is non-trivial. Basically, it's not simple. The example we had earlier about the rubber band is only applicable for very, very simple problems. But we know that the actual unit commitment problem is too complex for this. So it requires advanced methods. You have to go into the realm of exploring heuristics or meta-heuristics, whatever. Next is that the convex hull pricing does not follow typical economic dispatch properties. So that includes the non-binding constraints producing prices, offline units contributing to pricing. So that happens when a unit is partially committed, let's say, since the binary decision variables are relaxed now and from 0 to 1, it could be committed 0.2 or 0.3, which is weird, and that definitely contributes to pricing in CHP. Finally, convex hull prices changes for each time horizon. So here, we know the time horizon also contributes to non-convexity, especially for the end of period or the beginning of the period. So convex hull pricing takes that into consideration. So the prices for a 24-hour interval is different for a 48-hour interval or 12-hour or even 23 and so on. Lastly, convex hull pricing does include fixed costs, but the amount of fixed costs covered is inconsistent. So let's say you have a $100 no-load cost. The price reflecting the convex hull price may pay a portion of that fixed cost, maybe let's say 20%. But that 20% only applies to that specific problem formulation. If you change anything else, that 20% changes to maybe a value lower or higher than it. But what's important is it's inconsistent, which is an obstacle too if you want to do this in real-time operations.
Thanks, Jose. It's really important to understand the properties of convex hull pricing in order to really get a grasp on the difference between extended LMPs and traditional LMPs. So just in summary, to talk about some of the benefits of convex hull pricing, the primary argument made here is that it minimizes specific side payments. And what we mean by that, again, is product revenue shortfall and lost opportunity cost. It's important to note that there's a lot of other kinds of make whole and uplift payments out there. Talk about ancillary service payments, and there's specific units that have special runtimes. There's a bunch of uplift payments that aren't just PRS, LOC. Those are the only two that convex hull pricing claims to minimize. Beyond that, theoretically, CHP would improve the integrity for bidding strategies. The idea there is simply that a price structure that encompasses fixed costs and is just more descriptive of what's going on is going to make it more difficult for generators to kind of play the market, so to speak. In the same way, those more transparent cost structures would also help the efficiency of redispatch. So basically, load serving entities would demand power at different nodes, and since the cost of that power is has a better description of what that actually costs to produce that power, then you get closer to the market clearing price and the market clearing quantity. So as you get closer to the market clearing quantity, then you would expect that in the future the ISO could take that change in demand and then dispatch maybe a different array of units more efficiently to service all of the LSCs in the future. And then theoretically, kind of for the same reasons, then you'd have investors knowing kind of better what areas need to be upgraded, where the lines need to be added in the future. There are some shortcomings of convex hull pricing that have already been mentioned too. The biggest of which is the fact that CHP is time dependent. So it can only minimize those specific side payments if the commitment problem and the pricing problem are built over the same time horizon. And that's just not the case in industry. So the commitment model is usually run in a day ahead market and anywhere between a day and more in advance, where a lot of the slower generators need to be committed that long in advance because they have super long startup times, ramping, all stuff like that. And then convex hull pricing comes in later in a pricing model that's run much closer to real time in a real time market situation every hour, even more often. The problem is that at that point, since models have already units have already been committed, then convex hull pricing basically can't see the fixed cost of those units anymore. They become invisible. So it kind of becomes a chink in the armor of convex pricing being able to claim that it's minimizing specific side payments when it can't even see some of the costs that are related to some units in the system. Um, and then when it comes down to the difference between extended LMPs versus convex hull pricing has been mentioned before as well. Um, Convex hull pricing is still a mathematical and ideal idea. And in reality, it can't be implemented because we just don't have the computational resources to perfectly relax tens of thousands of constraints. It's just not possible. And so what you're left with is an ELMP, essentially a heuristic version of a convex hull pricing where you relax some non-convex constraints like unit commitment, startup, no load, stuff like that, and ignore others, maybe a really long min up and down times or multi-period ramping, like we talked about with rolling time horizons. Sometimes ELMP will also not include units that are virtually always on to increase the simplicity of the calculations. And it's really important to understand that once you start doing this in practice, you lose the claim and the provability that convex hull pricing makes that you're minimizing these specific side payments. In fact, not only are you losing the claim that you're minimizing side payments, you're losing the claim that you're reducing them at all. So it's actually possible for a traditional LMP to have lower specific side payments than the equal comparison ELMP that's going on there. There's other difficulties with implementing ELMPs, one of which is the fact that, as you can see in this graph, once an ELMP is implemented, you no longer have the guarantee that you'll have a non-monotonically non-decreasing price supply curve against total load. And essentially, when you have a traditional LMP, then you have generators submitting cost bids that are non-monotonically, or goodness, monotonically non-decreasing. And as a result, the LMPs themselves are also monotonically non-decreasing with increase in load. The problem is that ELMPs incorporating non-convex elements into the pricing mechanism can mess that up. And so what you can have is you can actually have parts of the supply curve that dip for an increase in demand, which is kind of deceptive for LSCs. You can decrease your demand and pay a higher price per megawatt, which is a little strange. Um, and then the kind of the final note with implementing LMPs is even if you were somehow able to prove that there's a reduction in specific side payments, that's an entirely different argument than claiming that total social welfare is increasing, which is much harder to show and prove. Essentially, what we're saying is even if these side payments are decreasing, sometimes that could actually result in what's essentially a wealth transfers that are happening between entities, and total social welfare is not actually increasing. It's actually impossible for total social welfare to increase based purely off of a pricing mechanism. So like a change from an LMP to an ELMP. If the dispatch is the same, total social welfare is going to end up being the same. That's really important to keep in mind. So what you're kind of left with is the argument that in the future, markets might change, incentives might change. The problem with that is that, as the professor likes to say, you change the game of poker, you're going to change the strategies. So it's kind of impossible to predict how the market will actually shift implementing ELMPs versus traditional LMPs. So in conclusion, what we found is that there's a lot of benefit and good positive out there from studying convex hull pricing. But given our current computational resources, right now, it may not make as much sense to implement extended LMPs over the traditional LMPs that we know function and work today inside energy markets.